right, so we actually got through the majority of the work in 2.2. So we just had a couple little things to cover to kind of keep us on track here. So that's what I'm going to cover here in particular, because I know there's a homework question kind of like number 8, and then 9 and 10 are really just more examples on things we've already done in class. So in number 8, we're asked to look at the 3 different graphs, so the graph of these 3 functions a, b, and c, and determine which one's the original function, which one's the first derivative, and which one's the derivative of the derivative, meaning the second derivative. So we can look at these and say, well, let's start off. Let's see if a could be the original, right? Well, a slope of a tangent line to a, let's choose a point here and say, oh, the slope of the tangent line, well, wait a minute, this is a line, right? So we would just be finding the slope. And if we look at a different spot, we would get the same slope. And if we look at a different spot, we get the same slope. So what would the derivative look like for this function? Well, it would be positive, first of all, right? All these slopes are positive. But it would be constant because all of these slopes are identical. No matter where I look, I get the same slope. So the rate of change, right, the derivative is the same everywhere. And so we would get some constant value. I don't know exactly what that would look like, but it would be a positive constant. So we would have something that looks like this. And I don't see any horizontal lines here. So what I know is that a's derivative is not graphed. So if its derivative isn't graphed, it certainly can't be the original function, because the original function is supposed to have a derivative, first derivative, and a second derivative. So a cannot go as the original function. In fact, it can't even be the graph of the first derivative, because again, its derivative would have to show up here somewhere. It's not here. So we know that a has to be the second derivative, right? Otherwise, its derivative would have to show up here. Okay, so we've classified a. So let's move on. Let's see if the original function might be b. So we're looking at the red graph here or the red function here for b, and we say, oh yeah, okay, it kind of has this curvature to it, and somewhere down here, I don't know exactly where, somewhere it kind of levels off. So if we think about what's the slope of the tangent line right there, right? The tangent line would come through like this. What's the slope of that? Oh, the slope is 0. Right, so if I get a point, and this happens a lot at mins and maxes, so if I look at the min for this function b, it looks like we're going to have a slope of 0. So we just have to figure out, well, if that's the original function, is its derivative here? So which of these functions, a or c, has a derivative, or has a value, sorry, at the same spot that's equal to 0? We go, oh, wait a minute, a. So a appears to be the derivative of b. Well, if that's the case and a is the second derivative, I guess b is not the original, but it's the first derivative function. And that would mean by default c is the original. So there's a bunch of things we could check, right? So we just checked one spot where the function, where the derivative, the slope, should be 0, and that lined up. But what else? Let's kind of make sure that a really is the derivative of b. Well, all right, if I choose a point over here, and I look at the tangent line, it's got a negative value, right? And that's going to be true for all of these ones until we get to that min point. And then it's going to flip around, and now the tangent lines are going to have positive slopes. So does a match that behavior? Well, sure enough, it does, right? So it's 0 right here. Before that, it's got a bunch of negative values. After that, it's got a bunch of positive values. So yeah, that definitely seems to check out. So the relationship between a and b is sound, but let's make sure that c actually checks out too. So we look at c and we say, all right, c is just kind of like a nice little wave coming in here. But what that means is it does also reach a min somewhere right around here, right? This is kind of like slowly, we got a little bit of negative slope right here, and just after that, a little bit of positive slope. But so somewhere in here, it has a tangent line that is horizontal, meaning its slope is 0. Oh, how convenient. B is equal to 0 at that very same value of x, right? So it sure seems like that checks out, and then we can even check the, the waviness. So after that place where the tangent line is horizontal, where the slope is 0, it looks like we have slightly positive values, right? The slopes are positive. Oh yeah, well, b, the red function, is a little positive. Before that, we get some negative slopes. And b, sure enough, is negative here, so it definitely seems like this relationship holds. All right. So 9 and 10, these ones I mentioned are really just expanding on some of the examples we already did in class. So this is nothing new as far as the content. It's just getting a little bit more exposure. So let's look at the first one here, 9. And this one has, right, if I plug in 1, that's always our first try, we're going to get 0 over 0. It's going to be something in indeterminate form. So, all right, that's not good. But we can use the property. We have this property, right, kind of like how a squared minus b squared is a minus b, a plus b. We'll use this in the denominator. The numerator is a cubed minus b cubed, a difference of cubes. There is actually a property for this as well, and it starts off with a minus b. Well, how do I get a cubed? I'm going to need to multiply by an a squared. Then I have, right, how do I get the b cubed? Well, I'm going to need to multiply by b squared. So there's my a cubed minus b cubed. But keep in mind, right, if we just FOILed this part out, we would have some extra terms in here that we don't really want to have. We'd have an a times b squared, and we have a negative b times a squared. So there's got to be some term in the middle that kind of balances it all out. I'm going to cut to the chase here, because you've probably seen this in pre-calculus at some point, but it's plus ab, and this should balance everything out. So if I distribute everything through, like for example, negative b times a squared, okay, that's negative a squared times b. I need to balance that with a positive a squared times b. Okay, well that's a times ab. There's a squared times b in a positive sense. So this is how it's going to factor. So then we're going to take our original. Okay, we're going to say, well, okay, I've started with a limit, x goes to 1, x cubed minus 1 over x squared minus 1. So if I apply those two properties I just wrote, then the top is going to look like x minus 1, right? X is taking the place of a, and you can think about this like x cubed minus 1 cubed if you really want to see this, and x squared minus 1 squared in the bottom. If you really want to see it as squares and cubes. So x is taking the place of a, 1 is taking the place of b. So x minus 1, then we got x squared plus a times b. Okay, well, 1 times x is just going to be x, plus b squared. So that's just going to be 1. And then in the bottom, this one we've done many times before leading up to this class. Right, so we get x minus 1, which is really the problem for plugging in 1. Those guys are going to cancel, which is great. So we say, well, this limit becomes a lot easier. X squared plus x plus 1 all over x plus 1. And hey, I can just plug that in, right? No problem plugging in 1. So we get 1 squared plus 1 over 1 plus 1. All right, so at the top I get 3, and the bottom I get 2. Bingo, bango, bongo. Right, so we got our little algebraic tricks to help us out here. Properties, I guess we'd call them, but they're tricks. Okay, so in the next one here, we're going to say, well, I've seen this game before. Remember to be careful. We are not going to infinity, so we're not going to play any little rules here, but we're going to multiply by the conjugate. And I might suggest, doing this separate of the limit. If you're going to do that, you got to be careful with your notation here. So if you just want to see what happens with the conjugate, you can leave the limit off for the moment, okay? And I'll show you how to pull that back in a way that is perfectly acceptable. Or you can do it as we've been doing, which is to leave the limit out front. I think that also is perfectly acceptable. So here's what we're doing. We're multiplying the top and the bottom by the conjugate of our numerator here. And what happens, this might be a case where if you want to write these things out, you absolutely can. But we know that we're going to multiply these first guys, right? So this times this, oh, it's the square root of the same thing, so that we're squaring a square root. So the square root symbol is going to be gone. We're left with just the meat inside. So we're left with x squared plus 36. All right, then we know if we multiply the outside terms and the inside terms, right? The whole point of multiplying by the conjugate is those are going to annihilate each other, right? Wipe each other out. We get a positive 6 times the square root, and then a negative 6 times the same square root. So those are gone. So then the only thing we have to worry about is the last terms, negative 6, positive 6. So that looks like minus 36. Ooh, that's looking good. Right? In the denominator, we got x squared, and then we have square root of x squared plus 36 plus 6. Also, if you hear sirens in the background, just ignore those. I don't live in a great neighborhood. So we have plus 36 minus 36. Those are gone. So our next stage is going to be x squared on top, x squared with our square root stuff on the bottom, plus 6, right? So here's what I'll say. Sometimes people go on a cancel fest, right? They cancel out the 36s, and then they cancel out the x squared. There's just like things are crossed out everywhere. Take the extra minute. Just write it out. It doesn't hurt to write those extra steps, right? So I'm going to cancel the x squared terms. All right, and then remember that on the top, this is like x squared times 1. You're not going to have 0. You're going to have a 1 up there. And then we're left with the square root of x squared plus 36 plus 6. All right, you can do all of this algebra, and then you can say, hey, I'm going to apply the limit. But you know what you would have to do in that case? You would have to give the original. You'd have to say, here's where I started. Here's where this is equal to, right? We did all the work. We showed all the stuff on the left side. This fraction got turned into 1 over the square root of x squared plus 36 plus 6. And then you could apply this, right? You could toss that in. So you say 1 over the square root of 0 squared plus 36 plus 6. All right, well, this is the square root of 36 is just 6, so this becomes 1 over 6 plus 6, or 12. So you could do this, right? You could kind of do your algebra separately if you don't want to carry through the limits. That's okay, but then you have to start back with the original. We can't just go, hey, all of a sudden I'm going to put a limit on here. Certainly not with an equal sign, right? So far, these steps on the left-hand side, these were all equal. We were just doing algebra. The alternative is, of course, you could just write out the algebra and then afterward go, okay, you know what though? I had a limit here. I had that limit, so it's going to hang out, right? You can just toss these in, and please be careful. Don't be lazy with your limits. Make sure that you are writing this stuff in. And notice we get to this stage, and all of these things, yes, are equal. And then we say, okay, cool, I'm going to plug in 0. We would end up getting to the same spot. We'd get to 1/12. I would want to show that intermediate step like I did here, but that's the basic idea.